Alright, so here's another word problem involving a vertical spring. So here we have a 0.35 kilogram mass. So there's a mass of a 0.35 kilograms. So the mass is 0.35 kilograms. And it is at rest, so the initial velocity is going to be 0 on a vertical spring, while the spring is initially compressed by 0.12 meters. So there's going to be a compression distance, which is going to be 0.12 meters. And the stiffness of the spring is 958. So the stiffness is equal to 958 newtons per meter. And the spring is initial, so if the equilibrium position of the spring is aligned with the ground level, so we're going to assume that x equilibrium is going to be at 0 at ground level. So if the equilibrium position of the spring is aligned at ground level, how high will the mass rise? So we're trying to find a final height. Once you release the spring and it's going to fly up in the air, how high will the mass rise? But in this case, if it experiences 2 newtons of friction, so there's a frictional force of 2 newtons, and while it's flying through the air, it experiences that frictional force over a distance. So I'm going to say that's going to be x friction, which is going to be 0.6 meters. So given that information, you want to find what is the final height. So let's see how to set up this word problem. So again, I'm going to have 2 coordinate systems, one for the mass and one for the spring. So from the mass's perspective, this is ground level, this is the height here. So the mass starts off on the compressed spring down here. And we're given the initial height of, starts off at rest, so the initial velocity is 0. And the initial height of the spring, so y initial here, is going to correspond to the compression of the spring. So the initial height of the spring is going to correspond to the compression distance, and technically if it's below the origin, we're going to assume that we're going to define that to be negative. So we have the initial value for the spring, we have the initial condition for the mass, and for the spring we have another coordinate system. So this is S for spring, and from the spring's perspective, it's compressed over this distance, x compression, which is the same as the initial height of the mass. And again, I'm going to define that to be negative. So both those values are the same. So that's the initial setup for the spring. And now the spring is released. So then at the final state, the mass, so this is the origin. And so in the final state, the spring goes back to equilibrium here. But from the mass's perspective, it flies into the air to some final height, y final, which is what we want. But while it's flying through the air, it experiences a frictional force that acts over a distance, x friction. So we're going to have to take that into account. And that's it for the mass, for the final state. So from the spring's perspective, at the final state for the spring, is it starts off being compressed, but then it just goes back to equilibrium here. So the final position of the spring is 0. And that's it for the spring. So now we have all the terms that we need, so we can go back to the conservation of energy equation. And in this case, the only terms that are going to remain, so let me just write down conservation of energy again. Conservation of energy, the full equation is work done by external force plus work done by friction is going to equal, I forgot to mention here, at the maximum height, final velocity is also 0. So work done by friction, and then plus the change in kinetic energy, which is going to be 1/2 m. the final velocity of the mass squared minus the initial velocity of the mass squared, plus change in gravitational potential energy, so mass gravity, final height of the mass divided by initial height of the mass, plus final height of the mass minus the initial height of the mass, and then plus the spring potential energy term, which is going to be 1/2 k. Big parentheses, and it's going to be final position of the spring minus initial position of the spring squared, minus equilibrium position of the spring squared, and then minus the initial position of the spring minus the equilibrium position squared. But here, there's a lot that we can simplify. There's no external force. The final velocity of the mass is 0. Initial velocity of the mass is 0. We're going to assume equilibrium position is 0. And in this case, the spring returns to equilibrium, so that means that the final position of the spring is also equal to 0. And so what we're left in this case is work done by friction. So that's going to be minus friction multiplied by the distance that the friction acts. And then that's going to equal gravitational potential energy term, which is going to be mass gravity, y final minus y initial, and then plus the spring potential energy term, which is going to be, there's a minus in front here, so it's going to be minus 1/2 k x spring initial, or the compression of the spring squared. And even here we can have some more simplification. In this picture, initial position of the spring, so I have it up here, initial position of the spring is the same as the compression of the mass, and they're both negative. So this equation is going to become minus friction multiplied by the distance that the friction acts equals, just write it out. So it's going to be mass gravity, final position of this mass minus the negative height of the mass when it's initially, when it's below ground. And then also minus 1/2 k, initial position of the spring is the same as the initial height of the mass, and squared. So now simplifying this equation, minus friction multiplied by distance that friction acts equals, we're trying to find y final, so I'm going to distribute the mg into both of these terms, so this is going to be mass gravity y final, and then plus mass gravity y initial, and then minus 1/2 k y initial squared. So we just have to solve this equation for y final. So mg y final is going to equal 1/2 k y initial squared minus mg y initial, and also minus friction times the distance that the friction acts. And we have to divide by mg on both sides, so the final height is going to equal 1/2 k y initial squared divided by mass gravity. Mass gravity divided by y initial divided by mg y initial is just going to be minus y initial, and then mass gravity divided by this term, which is going to be minus friction delta x over mass gravity. And so here we just have to plug in. It's going to be 1/2. The stiffness is 958. The initial height of the spring is the 0.12 squared divided by mass gravity, so 0.035 times 9.81, and then minus the initial height, which is the 0.12, and also minus friction, which is 2 newtons multiplied by the distance that friction acts, which is 0.6, and also divided by mass g again. And calculating that, that should equal a value of 16.5 meters.